Hi, and welcome to Directory Conversations, where we chat with our community of AI safety researchers. So, my name is Merim, and with me there is Chudo, and we will be co hosting today's conversation with Vanessa, Kosoy. And the directory that we're doing is a community of AI safety researchers sharing information about their research, finding collaborators, and inspiring others to build safe AI systems. So, our guest, as I have already said, is Vanessa Kosoy, an AI safety researcher at the Computational Rational Agents Laboratory, or CORAL. And thanks for joining us today, Vanessa. So before we start our conversation, could you briefly tell us about yourself and about Coral and what kind of work your team does?
Yeah, thank you for inviting me, Miriam and Judo. So I'm doing research in AI alignment for about 11 years, and the past 5 years it was like a full-time job. So Coral is a research group I created to work on the research agenda I built, which focuses on creating a formal mathematical theory of intelligent agents. And that's because I believe that this is the best way to sort of navigate the dangers of artificial intelligence in the coming decades.
Okay, nice. And it's interesting point that you say this mathematical approach would really be the best solution to the AI alignment problem that we have. So if you could more in detail explain the research you and others at Coral are doing and what kind of specific or peculiar benefit or value this research brings with regards to AI alignment.
Yeah. So I think that the alignment problem is a very hard problem, and like the reason it's, or like some of the reasons why it's very hard is because in some sense it is one shot. If you created something which is super intelligence, which is like high above human ability, and you did it wrong, then you lose control over the situation and there's no second chance. We're aiming at a very small target, like out of the space of all possible minds or intelligences we could imagine. Those that would be beneficial towards humans are a very small subset inside of this big space. So to hit this kind of small target in a one-shot setting, we need very robust and precise tools so that we know exactly what we're doing and have like very precise models of like how it's going to work and why. And I believe that this level of precision and robustness, it basically by design requires mathematical theory. And this brings us to the next level of the challenge, because there's also a lot of conceptually confusing philosophical issues. Like we don't even know how to formally define what it means, for things to be aligned. Like we're talking about alignment of values, but what are values exactly? What does it even mean for something to be an agent? So we're really what we're trying to do is like building this formal mathematical theory which would address those issues and ultimately allow having a formal mathematical definition of what alignment is, so that we can propose solutions for which we can prove, that they actually solve the problem.
Okay, thanks. Yeah, this precision is really lacking in the AI alignment field. I feel also, yeah, true.
All right, thanks, Vanessa. I'll jump in here with a few more questions. I have kind of very very specific questions. I'll go over them and then we can take them one after the other, if that's okay.
Sure.
In your article, in your article, the Lenin Theoretical Agenda Status 2023, you talk about the Lenin Theoretical Agenda, LTA for short, and Computational Superimitation, Kosoy for short. Could you elaborate on LTA and the key problems you're trying to solve with it? What insights do you have so far about these problems? How do your LTA research inquiries fit into the bigger picture of AI alignment? I'll stop there, and after that, I'll take a few more.
Yeah. So the Learning Theoretic Agenda is a research agenda I created with this goal that we talked about in the previous question of creating a formal mathematical theory of intelligent agents that can also define alignment in particular. This theory draws on a lot of existing research like statistical and computational learning theory, algorithmic information theory, control theory, game theory, like more recently things like applied category theory. And it's really kind of trying to identify where the gaps are between the sort of formal models and theories we already have and like the sort of theory we would need to have in order to answer those questions and to like achieve those goals. So I would say that the key problems, the way I would frame them today, are first of all, understanding what is the type signature of values. Like when we talk about agents that have particular values, how do we think about this mathematically? What is this object values? Like in some of the more classical approaches, like reinforcement learning theory, a value would be just some number that the agent receives or some function of its observations. But this is clearly not a very realistic and general model of what values could be. I could have values about things that exist in the world that I'm not observing right now, maybe won't even observe in the future. It can have values of things that will happen after I died already or something like this. So all of those things are not captured by the existing theories. So you're trying to understand what is the correct object here. Another key problem, which is sort of like parallel to that, is what is the type signature of beliefs, right? When you say that the agent has particular beliefs, or priors, or posteriors, and so on, what is the type signature of that? And here, there's similar issues of, do I only have beliefs? Pre-existing theories usually have beliefs in terms of beliefs about what the next observation that I will see is. But this is sort of in philosophy, that would be what's called logical positivism, where everything is formulated in terms of what I can observe. But there are other philosophical stances, kind of metaphysical stances that talk about metaphysical realism, things actually exist out there in the world, and you have beliefs about them. How do we talk about that mathematically in the theory of agents? And and the third key problem, which I would maybe third out of four key problem I would point out, is what are the formal mathematical conditions that allow us to call a particular system to say that it's an agent. And people in the literature would find things like Bayes optimality or things like regret bound conditions. But all of them are kind of not fully satisfactory. Either sometimes they are just computationally intractable, like Bayes optimality. If it's regret bounds, it does not take into account traps, like irreversible events or catastrophes that can happen in the environment. So there's no single mathematical criterion we can point at, which seems like it's the right thing. And then the fourth key problem, I would say, here is which spaces of world models admit computationally and statistically efficient algorithms. Because what happens is that currently we have things we have deep learning, which works great in practice, but we don't understand, like we don't know how to prove generalization bands about it mathematically. Then we have something like support vector machines, which which we know perfectly how to understand in theory, which we can apply in practice, but it's only very narrow in scope. It's only, you can learn very simple linear functions. And then we have things like Solomonov induction, which are kind of very general, can learn any computable process. We like have a theory about it, but it's completely intractable. It's incomputable. We cannot implement it in a real algorithm. So what's like the thing that sits between those three that we can also understand mathematically, prove generalization bands, has a wide array of applicability, and is also computationally efficient. This is kind of another, I think, central key problem. So so moving on into the insights we have about this problem so far. So I think we have several major insights that coming out of our research over the years. One is the framework which we call formal computational realism. It's previously called information physicalism, and we renamed it to formal computational realism. And it's like a framework that proposes answers to really the first three key questions I mentioned, like what is type signature of values of beliefs, and what is like the criterion of agency. And it's like a theory that is sort of like can be regarded as realism. We believe that that our theory should describe certain structures that exist out in the world, but here we're kind of formalizing the structures as information that the universe contains about certain computable information that the universe contains. And and this framework gives us some compelling answers to how agents can reason about things that are not tied sort of solipsistically or egocentrically to their own actions and observations. And there's also a particular condition of learning where learning happens not across physical time, but across the scaling of computing resources. We're kind of sort of approaching optimality as we scale the amount of computing resources in the system. So there's one big insight which we have, which is of course something still in development, but it's already taking shape. Another insight which we have is about the fourth question of so the fourth question of the rich space of world models. We have this direction which I call compositional learning theory, which is kind of trying to answer this question by looking for structures that exhibit compositionality and ways how learning algorithms can exploit this compositionality. I think we recently made very serious progress in this direction, which is it's still not published. It's like a paper in the works where working title was string logical sequence prediction, but I think we've had some very interesting insights there also. Did I cover the entire question, or did I miss something?
Yeah, you did. I think the last one was, how this all fits into the bigger picture of AI alignment, but
right.
As you went through.
Yeah. So how this fits into the bigger picture? Yeah. So I think the way this figures into the bigger picture is really that, I believe we are currently building AI systems wrong. I think that the sort of methodology and technology we are using today to build AI systems, where we have this stack of deep learning, and on top of it foundation models or large language models, on top of it reinforcement learning computing. I think that this whole kind of direction is not leading us to align the AI. It's leading us to bad things when we cross the superintelligence threshold. And and the reason is basically because we're just stacking things which we don't understand even individually on top of each other, and the aggregate of them we understand even less. And really, in some sense, I'm trying to find a different way of building AI. And this is how I think the theory fits in the picture, that using this theory, you can use it to invent new ways how to build AI, and how to make AI aligned. And and in particular, we have like Kosoy, which I think you mentioned, computational superimitation, which is what our current sort of, working hypothesis, best guess at what aligned AI looks like, and that is sort of emerging from our theory.
Great, thanks. And that's a great segue to the next question I had, because it's about Kosoy, computational superimitation. So could you elaborate on it a bit, its relevance to LTA and why you think it's important?
Yes. So computational superimitation is basically, so like I said, it's our sort of current best guess at what the ultimate solution might look like. It is an idea based on value learning, which is pretty classical approach in general in AI learning. We're trying to have the AIs to learn the human values or the values of the user, and then try to act on those values. So there are some classical approaches in that vein, like inverse reinforcement learning and cooperative inverse reinforcement learning. However, those classical approaches, they kind of suffer from like not having a clear model of what values are and what agency are in sufficient generality, and this causes them to have like very restricted applicability. So Kosoy is an approach where the AI kind of uses this formal computational realism-based framework to identify the user inside the universe as a particular algorithm about which the universe has information. So it's like if there is a program that the universe is running, and according to particular criteria, the AI can identify that this particular program is its user, and then like having identified this algorithm, it can sort of reverse engineer the values of the algorithm by sort of applying the inverse of this mathematical theory, right? So like if we have a mathematical theory which tells us 4, and this like addresses all sorts of forming conceptual issues, things like how to not incentivize the AI to sort of corrupt or temper with the user and make the user transform the user into something else. So this is like the sort of like conceptual difficulties that Kosoy is solving. And this is, and of course, this solution, it only can exist because of LTA. Like it's like deeply based, for example, on the FCR framework, which emerged from the LTA. So it's like tightly tied into it.
Great, thanks. So my next question is kind of related to, since after that work you did and the publication of your article, what has happened in the LTA landscape since 2023? What are some relevant developments since then, if any?
Right. So in 2023 we had like the big overview article about learning theoretic agenda. Since then, of course, there was a lot of work, a lot of progress. I will give just maybe some highlights of what are the most kind of prominent developments that have happened. So we put out 2 papers that we published on what we call information journalism, also in a kind of more academic language. We will call it robust reinforcement learning, or basically it's like combination of reinforcement learning with imprecise probability. We had like 1 paper on that in the Journal of Machine Learning Research called Imprecise Multi-Arm Bandits. Another paper which we presented this year in COLT, the Conference on Learning Theory, which calls robust online decision making, where we construct some general theory of regret bands for this information or robust reinforcement learning and show like apply to very special cases. There was a work by Gergely Such on how to use formal computational realism to solve the confusing problems about the interpretation of quantum mechanics, which we had the alignment forum post about, interpreting quantum mechanics in information physicalism, that's the old name of formal computational realism, which the importance is because like we think of identify quantum mechanics as sort of test case of philosophical confusions in which we sort of can test or our theories actually resolve, are actually good at resolving the sort of philosophical confusion we care about. It's not because like specifically quantum mechanics is important to AI, it's just more like a philosophical test scenario, and where I think we provided some very interesting answers. And there was another post called Information Handling by Hannah Gabor, who was my student in the maths, my mentee in the maths program. And information handling is an approach which we created to think about multi-agent interactions in using this robust reinforcement learning approach. There was a post written by Marcus Ogren, my spouse, called Non-Monotonic Information Physicalism, where like we had in the original post of formal computational realism, we had like this problem called the monotonicity problem, which imposed some very weird constraint on the sort of values agents can have. And then we further developed the formalism in a way which kind of avoids this. So this was kind of conceptually important development. Also a short form I wrote about the agency or learning criteria in formal computational realism. And of course, there is the work in progress, which I mentioned, the string logical sequence prediction, which I think is a milestone work in compositional learning theory, which is it's still not out, but where it's like in the works.
Great, thanks. Moving away from that research now, what are some directions for anyone interested in LTA and alignment research, right? What are a few directions you suggest they look into and why? And how would you measure progress as it relates to both LTA and Kosoy as a solution to AI alignment?
Right. So to the first question of which directions I would advise people to look at, so I think that someone who kind of wants to sort of independently understand and kind of maybe like contribute to some of the research directions, I would advise to focus on open problems that we mentioned, that we have in the papers that I mentioned before, the JMLR paper, precise bandits, and the code paper, robust online decision-making, and also in the open problems mentioned in the post called Information Physicalism, which introduced the formal computational realism framework. I think that those are good directions to focus on mainly because they there is a relatively well written up like explanation of what the open problems are, so someone can independently like read, understand what the open problem and even work on the open problem. Well, I mean, like that sort of tangentially. Also, if someone is like who is like, for example, a PhD student or a postdoc who wants to work on this research agenda, then I would recommend them signing up for the PIMS Summer Fellowship, which is actually happening very soon. Like the sign up is closing very soon, where I will mentor researchers to work on this research agenda. So there will be various research directions we can collaborate and work in there. I'm intending to do it next year as well. Yeah, in terms of measuring progress, that's a good question. So I think we have very generally measured progress on sort of like two correlated axes. Like one axis that you can look at is how many of the key definitions and theorems that we expect the final mathematical theory to have, we have already sort of found, and the other is like how many conceptually confusing philosophical issues which seem to be relevant to this we have already solved, and this are of course sort of tied to each other because the theorems and definitions are supposed to address the philosophical issues, but they're sort of complementary in the sense that in some areas we feel like we have conceptual clarity, relative conceptual clarity, but we're still missing technical work. So we see like that there's some missing theorems, like we want to like generalize results to particular settings, for example. And then it's like relatively easy to quantify how many missing theorems we have. And then like in other areas where there is less conceptual clarity, it's harder to quantify how many missing theorems we have, but it's easier to just point and say, okay, these are the conceptual issues which we haven't clarified yet. So for example, I think that there are issues which we have clarified pretty strongly, like which like so there was like various sort of puzzles in this area coming from the work of the Machine Intelligence Research Institute, like things related to Newcomb paradox and its generalizations, and things like the natural induction problem, and things like how you formalize a diamond maximizer. I think that those are questions in which we have gotten a lot of conceptual clarity using informationism and robust RL and formal computational realism. And on the other hand, there are issues in which we have less clarity, like for the multi-agent problems, which we have some ideas like information haggling I mentioned, but it's much like less clear what the answer is. And also what I call kind of descriptive or analytic and evolutionary agent theory, which is like the problem of how do you take an pre-existing system and sort of interpret it as an agent. Where we also have some ideas. We have this proposal called, for example, the algorithmic descriptive agency measure, which is mentioned in the article, but which are still in a very preliminary stage, and we still don't have like large confidence in like what type of answer really we're expecting to have there. And like evolutionary agent theory is like about how do you have like theorems about the emergence of agents, like the theorems that show that it's sort of selection pressure at a particular type of systems, which we call agents to emerge. Here again, we have like multiple ideas, but we don't have like a crystal clear picture answer. So yeah, so we're kind of measuring our progress along the axis and paradigms.
Our viewers go to learn more about Coral and the research you're doing, and is there anything else you would like to share with us and our viewers?
Yeah, so you can learn more about, so there is coral-research.org, which is Coral's website, where we also research outputs, like papers and the alignment forums we post. There is my user on the alignment forum, so Vanessa on the alignment forum, which you might find some complementary stuff, like some posts that give a little more background on how the papers connect to the overall alignment problem vision. And there are like the short forms I write, which are kind of less, much more terse and less, kind of finalized and really made rigorous and everything, but where you sort of like spit out ideas as they come along. Yeah, like people who want to do or interested in some like collaborations and things in that way, and are also welcome to email me at like Vanessa at alter.org. Yeah, that's are like the main ways.
Okay, then thanks a lot for today, like for joining us, for sharing about your research. I think it will be like really interesting direction for many people. Like it's interesting for me as well, but like I'm not researcher. Okay, thanks for today. Thanks for your time. And if anyone wants to join and be featured in these directory conversations, we would like to ask you to email us at aisafetyresearchdirector@gmail.com, and you can like talk about your AI safety research and chat with us. Thanks a lot for today, Vanessa, and have a nice day, everyone. Okay, bye.
Yeah, thank you for having me.
Okay, thanks.
Thanks. Bye.